Orthogonal properties of Legendre polynomial. Today we discuss about the orthogonal properties of Legendre polynomial. We have to prove that minus 1 to plus 1 pmx pnx dx equals 0 when m not equals n, and when m equals n 2 upon 2n plus 1. Okay. At first we talk about orthogonal function. What is called orthogonal functions? Okay. We define orthogonal function as the inner product of two functions f and g with respect to non-negative weight function w over an interval a and b. This take as closed interval. Okay, here f and g are two functions and w is weight function. We consider this as this weight function as 1 in simple case. Okay, this is the definition of orthogonal function a to b f of x g of x to w of x dx. Okay, we say that functions f and g are orthogonal if their inner product equivalently the value of this integral is 0. Okay, two functions f and g, and we integrate this over a closed interval a and b. If we get 0, then we say that this is as orthogonal function. Okay, this is taken as orthogonal function. Okay, here we take an example. The two function 2t plus 3 and 45t square 90 minus 17 are orthogonal with respect to a unit weight function. If we take unit weight function, then we take here 1. Then we take here as w of x is considered as 1. Okay. Then the interval minus 1 to plus 1. So 2t plus 3 we take here as the product of two functions 2t plus 3 into 45t square plus 90 minus 17 into 1. This is weight function dt equals 0. Then we talk about the Legendre polynomials orthogonality of Legendre polynomials. The Legendre polynomials are orthogonal with respect to the uniform distribution on the interval minus 1 to plus 1. Okay, the distribution here, the distribution is taken as uniform distribution. Okay, and the interval is minus 1 to plus 1 closed interval. Okay, this is taken as simple case and we get 0, and other case 2 upon 2n plus 1 when m equals n. Okay, we prove this. Okay, we prove this. Okay, at first we prove the condition is m not equals n. When the condition m not equals n, we prove this. We know the Legendre differential equation. Legendre differential equation, that is 1 minus x squared d square y upon dx squared minus 2x dy upon dx plus n into n plus 1 into y equals 0. This can be written as d dx 1 minus x squared dy upon dx plus n into n plus 1 into y. If we differentiate this, we get the previous equation, previous line. Okay, d dx 1 minus x squared dy upon dx. This is my first and that is second. if we differentiate this with respect to x, we get this is my first function into the differentiation of second, that is d square y upon dx squared, and first differentiation of first function is dt dx of 1 minus x squared is 2x. This is my minus 2x into dy upon dx, and that is n into n plus 1 into y, that is the previous one. This equation is considered as equation 1. Okay, since we have to prove pm x pnx dx over interval minus 1 to plus 1. Since pmx and pnx, we take it as pnx and pmx. Pmx are solution of equation 1. Therefore, we get d dx 1 minus x squared d, this y is pnx, pn, and we take this pnx as pn upon dx plus n into n plus 1 y pn, y is here as pn equal to 0. This is equation this is okay 2, and the third d dx 1 minus x squared d pm upon dx plus m here as m, n here as m plus 1 pm equal to 0. That is equation C. Okay, here we see that this is my pn, this is my pm, this is pn, this is pm. We multiply equation 2 pn by pm, and equation 3 by pn, then we subtract that. Okay, equation 2 into pm minus equation 3 into pm pn, then we get d dx 1 minus x squared dpn upon dx, this is pm multiplied by pm, and minus d dx 1 minus x squared dpm upon dx into pn. Then here we take plus if we multiply pm in that equation, we get n into n plus 1 pn pm. So we can write here in here as this is pn and this is pm equal to 0. Here n into n plus 1, minus m into m plus 1. Okay, pn into pm we take here as common. Okay, then integrating this over an interval minus 1 to plus 1, and we get, okay, we write here integrating with respect to x between minus 1 to plus 1. Okay, Here we integrate this with respect to x between -1 to +1. Okay. Just integrate that terms. Okay. Okay. This is my okay. We write this as integrating -1 to +1 d dx 1 minus x squared dpn upon dx pm dx minus integration d dx -1 to +1 1 minus x squared dpm dx pn dx plus n into n plus 1 minus m into m plus 1 pn pm dx is equal to 0. Just we integrate this over interval -1 to +1 or between -1 to +1. Okay. Here we consider this as first. This is first and this is second. Okay. So integrating, we integrate uv then we can write u into integrating of v minus differentiation of u into integrating of v whole integration over the limit. Okay. So this this term, this is pm, we write this pm. If we integrate this with respect to x, this and this cancel out and we get 1 minus x squared dpn upon dx. Okay. And our limit is -1 to +1. Okay, this is first term. And the second term we get okay, for that it is integration -1 to +1 differentiation of pm d dx of pm into integration okay, 1 minus x squared dpn dx with respect to x. Okay, this is this total d dx 1 minus x squared dpn upon dx is my second function. Okay. So we get here 1 minus x squared dpn upon dx and we integrate with respect to dx. Okay. So plus okay, this is minus, this is minus, okay, this is minus, we integrate this, we get pn 1 minus x squared dpm dx. Okay, -1 to +1 and the second one, that is -1 to +1 d dx pn 1 minus x squared dp m upon dx into dx. Okay, and the last term, this is this is a constant, so we take this outside the limit, plus n into n plus 1 minus m into m plus 1. Okay, into integrating -1 to +1 Pn Pm dx is equal to 0. Okay. So here, if we put this limit, we get 1 minus x squared minus 1. Okay, we write here Pm 1 minus 1 dpn upon dx. This is 0, and minus Pm 1 minus that is 1, 1 minus into minus 1, that is minus 1 into minus 1, that is 1. Okay, plus 1 square as minus. Okay, dpn dx, that is here and here we get 0 as 0. Here 0, here 0, here and here is minus and plus, that is we get 0. Okay, so and that term we also get 0. So we have just only that term n into n plus 1 minus m into m plus 1 integrating minus 1 to plus 1 Pn Pm dx is equal to 0. Okay, every term okay, we get here as 0 because this integration is taken as minus 1 to plus 1 limit. Okay, so here we get n into n plus 1 minus m into m plus 1, okay, into integration between minus 1 to plus 1 limit Pn Pm dx is equal to 0. Here n into n plus 1 minus m into m plus 1 into something is equal to 0. This can be happen when this term and this term both is equal to 0, or either this or that term is equal to 0 here, but m not equals n, so this term not equals 0. n into n plus 1 minus m into m plus 1 is not equals 0 because m not equals n. So my 0 term is this Pn Pm dx is equal to 0. Therefore, minus 1 to plus 1 Pnx Pmx dx is equal to 0. This is the proof of that Pnx Pmx dx is equal to 0. Okay, and we prove the second one 2 upon 2n plus 1. Okay, okay, the second one is integration minus 1 to plus 1 Pn sorry that is Pnx whole square dx is equal to 2 upon 2n plus 1. When m equals n, we get just Pnx. raised to the power 2 dx equals 2 upon 2 n plus 1 when m equals n. Okay, that is the second one, that is minus 1 to plus 1. We write this as pnx a squared dx. Then okay. So we know that 1 minus 2xz plus z squared raised to the power minus half is the generating function of Legendre polynomial of first kind. Okay, we know that. So okay, we can write for n 1 minus 2xz plus z square raised to the power minus half pnx z to the power n, and we similarly we can similarly write 2xz plus z square raised to the power minus half this m to m equals 0 to infinity pmx z to the power m. This is equation 2. Okay, we multiply these 1 and 2 on both corresponding side. Okay, multiplying corresponding of equation 1 and equation 2. Okay, corresponding side we multiply here in the corresponding side just. Okay, we get if we multiply this we get 1 minus 2xz plus z square raised to the power minus 1 minus half into minus half into minus half, that is plus 1 that is minus 1. Okay, this is plus, sorry, minus half plus minus half, that is minus 1. Okay, sorry, equals uh, this and this. Okay, that is m equals 0 to infinity, n equals 0 to infinity. Okay, pnx pmx z to the power m plus n. We multiply this, so the power is taken as plus m plus n. Okay, index is taken as the sum. Okay, we integrate this minus 1 to plus 1. We have to prove this, so we integrate this from minus 1 to plus 1. We 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 have to see this term by this. Okay, so integrating with respect to x between minus 1 to plus 1, then we get minus 1 to plus 1 minus 2xz plus z squared raised to the power minus 1 dx is equal to summation m equals 0 to infinity n equals 0 to infinity pmx z to the power m plus n dx. Okay, then we can write this as 1 minus 2xz plus z square. Okay. Okay, we multiplied this by minus 2z and divided by minus 2z dx. M equals 0 to infinity, n equals 0 to infinity, pnx, pmx, z to the power m plus n dx. Okay. Now, okay, if we differentiate this, we can get minus 2z. So this can be written as minus 1 upon 2z. Okay, ln of this natural logarithm of this 1 minus 2xz plus z square. Okay, this minus 1 to plus 1. We know that integration. Okay, is taken as ln x. Here differentiation of x is equal to 1 into dx, that is ln x, one natural logarithm of x. Here 1 minus 2xz plus z square, the differentiation of this is minus 2z and that dx. So we take this as ln of x, that is 1 ln of 1 minus 2xz plus z square. Okay, equals here if m equals n, we can write n tends to the n equals 0 to infinity, pnx into pnx, that is pnx raised to the power 2, z to the power twice n, m plus n, that is n plus n, that is 2n dx. Okay, so if we put this limit as this function, okay, we can get minus 1 upon 2z natural logarithm 1 minus 2z plus z square, 1 minus 2z plus z square. We can write this as 1 plus okay, 1 minus z square, 1 minus z whole square minus okay, when we put there is minus okay, natural logarithm minus 2xz, that is minus, and minus, that is plus 2z, that is that is 1 plus z raised to power 2, that is 1 plus z whole square, equals n equals 0 to infinity pnx whole square z to the power twice n dx. Okay, just we put this limit in that. Okay, we get minus 1 upon 2z. We can write this 2 at here, 2 natural logarithm 1 minus z minus natural logarithm 1 plus z. Okay, this 2 here, and we take this 2 as common. Okay, because n equals 0 to infinity pnx whole squared z to the power twice n dx. Okay, okay, then we multiplied that, we can minus 1, we get 2 and 2 get cancelled, that is, and we multiplied this minus 1 through this. Okay, we get natural logarithm 1 plus z minus natural logarithm 1 minus z, okay, equals n equals 0 to infinity pnx whole squared z to the power twice n dx. Okay, okay. So we know natural logarithm 1 plus z equals we expand this. Okay, that is uh, uh, 1 upon z, 1 upon z, 1 upon z into natural logarithm 1 plus z equals z minus z square upon 2 plus z cube upon 3 minus z power 4 upon 4 plus dot 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 minus, this is written as minus z square upon 2 minus z cube upon 3 and so on, z power 4 upon 4 dot 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 equals summation n equals 0 to infinity pnx squared z to the power twice n dx. Okay, here z plus z minus minus plus, there is 2z, 1 upon z, z plus z, that is 2z, and z is minus z square by 2 minus minus plus z square by 2, that is 0, that is 0, this term 0 vanishes by that. Then z cube upon 3 plus z cube upon 3, that is 2z cube upon 3, and so on, 2z cube z to the power 5 upon 5 plus dot 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 dot, and the last term is 2z to the power twice n plus 1 upon twice n plus 1. Here 5, here 3, here 5, here and here 2n plus 1, because when z to the power 5 we divide by 5, so 2n plus 1, when 2n plus 1 power, then we divide 2n plus 1, okay, as the denominator. Here z z to the power 1 1 3 5, so the 2n plus 1 okay, and uh, equals n equals 0 to infinity pnx raised to the power 2 z to the power twice n dx. Okay, okay, we divided through z, through this line by z, equals, we get 2, we take 2 as common, 2 into, that is okay, 2z, okay, mm, that is 1 plus z square upon 3 plus z to the power 4 upon 5 plus dot 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 dot, and the last term is z to the power twice n divided by twice n plus 1 equals n equals 0 to infinity pnx raised to the power 2 z to the power twice n dx. Okay, okay, we write this as, write this series as n equals 0 to infinity z to the power twice n upon 2n plus 1. If we put n equals 0, that is z to the power 0, that is 1, and that is 0, plus 1, that is 1, that is first term, and 2, that is 2 into 1, that is 2. Okay, so this is right for this series equals n equals 0 to infinity, n equals 0 to infinity, pnx whole squared z to the power twice n dx. Then we can equate coefficient of z to the power twice n. We can write equating coefficient of z to the power twice n. Then we get minus 1 to plus 1 pnx raised to power 2 dx equals 2 upon 2n plus 1. Just this and this can be equated. Okay, so then we get pnx whole square dx equals 2 upon 2n plus 1. This is the orthogonality of Legendre polynomial. So here this we write orthogonal properties of Legendre polynomial এখানে first line, second, third and fourth. Okay, thank you.